You trust the floors beneath your feet every single day. You step onto hotel balconies, sky bridges, and suspended walkways without a second thought. But what if the only thing keeping dozens of tons of steel and concrete in the air was a connection that was never properly checked for the actual weight it would carry? On July 17, 1981, that question received the most devastating answer possible in the atrium of the Hyatt Regency Hotel in Kansas City, Missouri. The Hyatt Regency was brand new, just a year old, and it was stunning. Its centerpiece was a soaring atrium, open, airy, and connected by 3 suspended walkways on different levels. These walkways weren't just functional, they were architectural statements, elegant paths floating in space, giving guests breathtaking views of the lobby below. People loved walking across them. They felt modern, they felt safe. At approximately 7:05 p.m., those watching from above heard a loud popping sound. Then, without warning, the 4th-floor walkway dropped several inches, paused for a terrifying moment, and then plummeted downward. It crashed directly onto the 2nd-floor walkway below it. Both structures, now joined in destruction, smashed into the crowded lobby floor with massive force. The sound was deafening. Dust and debris filled the air. Water pipes burst, flooding the scene. In just seconds, 114 people lost their lives and 216 more were injured. It remains one of the deadliest structural collapses in American history. How could something like this happen in a brand new building designed by professionals? The answer lies in a seemingly small change made during construction. A change that altered the load path in a catastrophic way. To understand what went wrong, you first need to understand what engineers mean by load path. Load path is simply the route that weight and forces take as they travel through a structure down to the foundation. Think of it like a chain of people passing heavy sandbags down a line. Every single link in that chain has to be strong enough to handle the full weight at that point. If one link is weak, the whole chain breaks. In the Hyatt's original design, the walkways were to be supported by long, continuous steel hanger rods. These rods would run from the roof structure all the way down, passing through the 4th-floor walkway beams, and then continuing down to support the 2nd-floor walkway. In that design, the connections at the 4th floor would only need to support the weight of the 4th-floor walkway itself. The 2nd-floor walkway hung independently further down the same rods. But during construction, the steel fabricator proposed a change to make assembly easier. Instead of one long, continuous rod, they suggested using 2 shorter rods at each connection point. One rod would hang from the roof to the 4th-floor walkway. A separate rod would then hang from the 4th-floor walkway down to the 2nd-floor walkway. The engineering firm approved this change. On paper, it seemed minor. In reality, it completely changed the load path. Now, the connections at the 4th-floor walkway had to support the weight of both the 4th-floor walkway and the entire 2nd-floor walkway hanging beneath it. The load on those critical connections had essentially doubled. The walkways themselves used box beams. Think of the box beam like a diving board. A diving board is designed to flex under the weight of one person at the end. But what if suddenly 2 people were standing on it and the fulcrum point had to hold both? The connection wasn't designed or strengthened for that doubled responsibility. When investigators from the National Bureau of Standards later tested the actual connections, they discovered something shocking. Even the original design was marginal. It only provided about 60% of the strength required by the Kansas City Building Code. But with the change, the connections at the 4th floor were so weak that the walkways had barely enough strength to support their own weight, let alone the weight of people standing on them. On that crowded evening, the additional load was enough to push the connections past their breaking point. The box beams began to deform and crush around the washers. The nuts pulled through the steel. Once the first connection failed, the load shifted violently to the others, creating a rapid chain reaction. The walkways didn't just fall, they tore themselves apart as they went down. This disaster wasn't caused by bad steel or poor workmanship in the field. It was caused by a failure in the design verification process itself. The change was made for practical construction reasons, to avoid having to thread long rods all the way down, which was difficult. But neither the fabricator nor the structural engineering team performed new calculations to verify that the modified connections could handle the new forces. Communication broke down. Responsibility for checking critical details became blurred. The engineer of record for the project later took responsibility for the systemic failure in oversight. The consequences were swift and far-reaching. The engineering firm lost its license in several states. Key individuals faced legal and professional repercussions. But more importantly, this collapse became a turning point for the entire structural engineering profession. Before 1981, it was somewhat common for engineers to delegate the detailed design of connections to fabricators and only review them lightly. After the Hyatt Regency disaster, that changed forever. Today, structural engineers are required to take explicit responsibility for reviewing and approving all critical connection details shown on shop drawings. Load path analysis must be thorough and clearly documented. Any changes during construction, no matter how small they seem, must be re-evaluated by the designing engineer with full calculations. The concept of a clear, unbroken load path is now drilled into every engineering student as a fundamental principle, not just a technical detail. The next time you walk across a sky bridge in an airport, or stand on a hotel mezzanine, or cross a suspended walkway anywhere in the world, remember this story. Those structures feel safe because of lessons learned in tragedy. Because engineers now understand that the most dangerous mistakes are often the ones that look like simple conveniences on paper. This is why we tell these hidden stories of engineering. Not to frighten you, but to show you that the safe world we live in today was built through hard lessons, careful thinking, and the courage to learn from failure. If this story made you think differently about the structures around you, hit that like button. Share it with someone who needs to hear it, and subscribe to Hidden Stories of Engineering, where we uncover the forgotten decisions, the quiet failures, and the brilliant fixes that shape our modern world every single day. Thanks for watching. Stay curious and stay safe.